Okay, so we've got a couple different cases here for different potentials to confine our particle in, and we mentioned that it would be useful to see the wave function plotted on top of the potential so you can see how it's being confined and how much it's tunneling and so forth. And it'd also be useful to have a visual representation of where our current energy level is with respect to the potential. So that's what we're going to do in this video. And we're just going to start by deleting our second graph because we want everything to be on the same graph. And we can plot multiple plots on the same graph by building an array where each array is the cluster of x and y points for a particular graph. So let's get our potential here. And the potential is just something we're going to plot actually unaltered. So I'll just go ahead and wire that straight in there. The wave function we're going to need to scale. So the thing is our potential was on the scale of thousands because our depth was in thousands. But our wave function is on the scale of some number less than 1 because its probability is normalized. So we actually need to scale the wave function in order to get it to plot right. So, actually what I'll do is I'll keep this plot of just the wave function with its proper axis here because that'll come in handy later. And we'll make a second graph, which is kind of everything overlaid on top of itself. So, okay, so first thing, we've got the potential. We also want to plot the energy level, and we'll do that as like a straight line here. So easy way to do that is to initialize an array, because you have to plot an array of points. And the size of this array will be the size of however many x points we have. So we'll do an array size here. There's our x points. Let's put those labels on so you can see what I'm working with. That's the dimension size. And we want the y value to be our energy. So I might have to reorganize these wires here later because we're going to have some crossed wires, which I don't really like. But this is fine for now. So there's our y values of our energy level. We need to bundle that with the x values of space that we're plotting everything over. We'll plug that in, and then let's go ahead and graph that just so we know what we're doing here. Okay, so now we've got our potential in white and our energy level in whatever that color is. Currently should be at negative 1882. That looks right. And if we shift to find an excited state, there we go. We found another energy level that's way up there. Okay, so that's useful on its own. Now we want to put the wave function on top of that. Okay, so the first thing we want to do is we need to scale the intensity of our wave function so that it's visible on this scale. And in order to do that, first you need to normalize the intensity of your wave function, whatever it is, to something that you know. And so we're going to make the maximum of the wave function be normalized to 1. And how you can do that is you can take this array min and max. You can take your wave function array, which is right here, coming out of our inverse power iteration loop. And you can divide the wave function, every element in the wave function, by its maximum value. And that will make the maximum value 1. Now we can multiply it by whatever we want its final intensity to be. what do we want its final intensity to be? Well, it depends on what kind of potential we're looking at. And the goal is we always want it to show up on this Y scale, no matter what we have it set to, because maybe we have it set to like, over twice this. And we still want our wave function to appear. So we actually want to read what the current scale is on that graph. So I'm going to right click on it, create a property node, because that's how you read properties of front panel objects. And we're going to go to the Y scale and the range. And we'll start with the maximum, but we also want the minimum if we drag down there. The maximum minus the minimum is the total height of our Y axis. And let's always make our wave function be maybe 1/10 whatever the current scale is. And that's just a number that kind of tends to look nice and make it visible, but not take up the whole graph. So now we can take our wave function and multiply it by that value. And then we can bundle that with the x values once again, which is way over here. And there we go. And we can, let's see if that works. It does work. However, our wave function is still, it's at 0. We want it to actually be shown at whatever its current energy is, which is down here, shifted by the eigenvalue. So we just need one more step here. Let's insert a subtract. We want to, or actually we want to add it. Our energy level. And then we'll try that. There we go. Now it's in the right spot. And if we shift to find an excited state once again, cool, we've got the wave function shifting with us. So this is useful because you can see how the wave function's confined. You can see it tunnels more as you go higher up in the well. And you can kind of see, like, is the wave function going to be able to escape the well soon, and so forth. So that is how you do that. We want to make this all a sub VI, just to clean all of this crap up here. So just kind of organizing this so that we can select it all. And in the process, make it messier, but bear with me. Just going to group everything here. We've got all of these inputs. We've got our, just make sure we don't have anything in here we don't need. Move that down. Yeah, let's just bundle this all together. So if I select all of this, our output is going to be this clustered graph. Our input is going to be the energy, our x values, or nope, our wave function, sorry, and our x values. Currently, we're actually reading the x values twice, so let's just connect these arrays so that it knows not to duplicate inputs. Okay, so we'll have our x values, we'll also have our potential, our wave function, and our energy. That seems good. Let's make that a sub-VI. Oop. We can't. What if we... Oh, did I deselect it here? Okay. Here we go. Create some. Just got to click on the edit of the block diagram. Cool. All right, so you'll notice one thing this did is it created this little deal here. And if we open up our sub-VI, and I can clean that up now. We've got this X graph in input. This is a reference. It references some control on the front panel of the parent program. So this is currently referencing xgraph2, but say I wanted to do the similar sort of processing to xgraph no number, I could change that reference to reference some other graph on my front panel. So I could actually copy this sub-VI many times and use it to format many different graphs, as long as I'm referencing a different control, if that makes sense. Okay, so that's how we do that. One more thing actually I want to do in this video is just add an option here for say you don't want to plot the wave function, but you want to plot the probability distribution. This is actually just the wave function, not a guess. In that case, we want to have the option to square the wave function right here. So let's actually make a case structure. And also some control. So let's have like a true-false control for if we want to look at the probability distribution. Probability. So if that's on, we'll look at the wave function squared. If it's not, it'll just be the wave function. So in the true case, we'll square everything. And in the false case, we won't. And then what we need to do is we need to bring this to our main program as well. So we'll add a input there for probability. We'll create that on our front panel of our main program. And now when we run it, let's see what happens. Let's go back down to our ground state because we know what it's going to look like, and turn that on. That squares it. Nice. Cutting it off a little bit there. Go to our excited state. So now we have some negative stuff. Square that. Cool. All right, and that's how we can make these nice potential energy graphs with the wave functions overlaid on them.